Hi guys, Mr. Kane here. Nice to see you again.
Hi, it's Mrs. Goswish. Mr. Kane, what's on your board now? Last time it was Chem's Try. What's there now?
A bunch of numbers, random numbers, 9, 16, 10, 13, 11, 10.
Is that the lottery numbers?
Maybe the lottery numbers if you're a big winner.
Awesome. Yeah. Do I have to share if I win?
Only with me.
Okay. I can live with that.
All right. Here we go. Atomic History Part 2. In this part of Atomic History, we'll talk about Ernest Rutherford here. Ernest did his work primarily in 1909, 1910, and he actually happens to be a former student of...
J.J. Thompson. So the student becomes the teacher.
Yeah, basically, yeah. I guess that means this guy's British also.
Aren't they all?
They seem to be. Basically, what he did is he performed an experiment to change the view of the atom again, and what do you know, just like J.J. Thompson, he wasn't trying to do chemistry, he was trying to do physics at the time.
All these physicists.
Yeah. The interesting part about being a college professor, he's actually a college professor, not a high school teacher, is that he gets to use his grad students to do his work for him. He finds something funny and he says, hey Geiger, hey Marsden, go do this for me.
The grunts of the academic world.
Sometimes it pays off, though, because we do know Geiger's name these days.
Oh, is he the Geiger counter guy?
He's the Geiger counter guy, exactly.
Didn't know that.
Radioactive sort of guy. All right. So I guess the first thing that we've got to do is we've got to talk a little bit about radiation. Geiger might have given you the idea that, that we have to talk about radiation. It turns out that radioactive elements spontaneously decay into pieces. These pieces could be several things. They could be alpha particles, which this is the one that you've got to know. Alpha particles are made up of two parts. They're made up of two red parts and two blue parts.
So the red parts are protons and the blue are neutrons. So that alpha part?
They're just red and blue, that's all.
Oh, okay.
It has nothing to do with protons and neutrons. What are you talking about?
Well, I'm just kind of reading the legend there, and it looks to me like an alpha particle has mass and a charge.
Oh, yeah, okay. So sometimes we can write alpha particles this way. We call them helium nucleuses because they've got two protons in them in a total mass of 4.
And a proton is a positively charged.
Oop. And this is actually positively charged. Yeah, you're right.
Yeah.
So it's got a positive 2 charge. So these guys, if we had these in a cathode ray tube, what do you think they'd do?
If they were in a cathode ray tube, they'd probably repulse anything negative. No, attract anything negative.
Yeah,
Opposites attract, right?
So if I brought the negative end of a magnet in, it should attract.
Yeah.
Which is the exact opposite of what the electron does.
That's right. Opposites attract, like repulse.
So that's the big deal here, guys. You can also get out gamma rays, which are pure energy, and you can get out some beta particles too, those beta particles which are called electrons. But the big deal here is what Geiger, Marsden, and Rutherford were working with.
They're going to use alpha particles, aren't they?
Matter of fact, here's a picture of what they did. They did an experiment with our favorite element.
Gold.
Gold.
I love gold.
All right. So basically the setup is this. They take this, they take a block of lead and they put inside of it an alpha particle emitting element, and what they happened to use was
Polonium?
Polonium. Yeah.
So they had a radioactive element in a block of lead.
Mm-hmm. Okay. And they've got a little hole in the front of the block of lead so that the only place that the alpha particles can actually get out is through that little hole in the front. So they've basically built a gun out of this with its constantly firing alpha particles across. And what they're doing is they're firing it at this very thin piece of gold foil. Why did they make a piece of gold foil, Mrs. G?
They used gold because gold is one of the metals on the periodic table, and metals are malleable and ductile, and you can make it nice and flat. So gold, aluminum, any of those that are metals can be smooshed into a nice thin piece of foil.
Oh, okay. So you probably only got a few atoms thick in that gold foil, huh?
Yes.
They put this screen around the end, and they call it a detecting screen, basically because any alpha particles that hit this detecting screen, it's got a special chemical on it that lights up when an alpha particle hits it. What they were expecting was all of the light to be over here because they thought that atoms were plum pudding.
That's
and that
the Thompson model,
they
right?
They were neither positive nor negative, so something positive trying to fly through them would just fly right through. No problem at all. It turned out, though, that the picture that you see here, that they saw these deflections, and I think we've got a good video showing how these deflections work.
All right.
Let's go to it.
In 1910, Rutherford and his co-workers were studying the angles at which alpha particles were scattered as they passed through a thin gold foil. Most of the alpha particles passed through undeflected. However, a few were found to be scattered at large angles, some even back in the direction from which they had come. This meant that they had collided with an object much more massive than the alpha particles themselves, yet so small that only a few alpha particles encountered them. This atomic level view shows what is happening. Most of the atom is occupied by the low mass electrons. The nucleus is small and massive. When an alpha particle encounters a nucleus, it is scattered at a large angle.
All right, so conclusions of the gold foil experiment from the YouTube video and what we just said. There must be empty space between the atoms.
The reason why there must be empty space is because some of those alpha particles actually got through.
Which makes sense. If there's empty space, they passed on through, which is what they expected, right? They expected all of the
They expected
alpha
all
particles,
of them to get through.
all the alpha particles to go through, but what they got was some of them bouncing back at them.
So that they're supposing that something must be interacting with these positive alpha particles.
So that something is what they figure is there must be something small and massive in the center of the atoms, right?
Mm-hmm. Yeah. And they worked out that that's approximately 1/10,000th. That small positive thing is 1/10,000th the size of an atom. That's basically saying like a sports stadium, like Soldier Field. That's like saying that the whole thing is an atom, and that the nucleus of the atom, the small positive thing, is the size of a marble.
In the center of the field.
Yeah, on the 50-yard line.
Okay.
Yeah. So that's an extremely small little piece when you really think about it. One of the things that they came up with was that the nucleus has to be larger than the alpha particle because they knew the alpha particle had a bit of a charge, but not a lot. And they knew that the nucleus had a lot more charge because it wasn't actually getting deflected anywhere.
Okay. Is that what it would look like, Mr. Kane?
Yeah, that's an artist's interpretation of what Rutherford's model is.
The blue things are electrons?
Yeah, and the red and white things are the nucleus, so I guess those are all protons in there.
Okay.
So, my only problem, well, I've got one problem with this. You know what? Come to class tomorrow and give us at least one problem with this particular model.
All right.
All right, so that's an assignment. So you'll see some words up there, assignments. So you're going to have to brainstorm that. So this utilizes the Thompson model. There's some modifications here. The atom's now mostly empty space. The positive nucleus is extremely small, and the electrons are separated from the protons. So we don't have any corpuscles inside of pudding anymore. We don't have any electrons inside of pudding.
Thompson's model is gone. It's been usurped by his student, Rutherford. And Rutherford says there's a little core, a little heavy pit at the center of an atom. Oh, like a peach pit.
Kind of like a peach pit, yeah.
All right.
Or a cherry pit.
Core nucleus that's positively charged with protons, and the electrons are around the nucleus?
Yeah, they're going around
moving
it.
around?
If I remember right, didn't he call this like a space system model or a...
I'll bet he called it the solar system.
Okay, the solar system model. So the electrons are kind of moving around in concentric circles.
Oh, okay.
Okay. All right, so there are some positives here, some kudos. The protons and electrons allow for neutral atoms. That's a nice thing because we know that matter isn't made up of just negative matter.
Right.
The spacing of the protons away from the electrons explains what we've seen in the gold foil experiment, but we still have some problems here.
The mass of an atom cannot be just protons and electrons. The problem with the having just protons and electrons is why aren't the electrons being attracted right to the nucleus then? What's keeping them apart? Opposites attract. If the protons are the nucleus and they're positively charged and the electrons are negatively charged, how come they're not smooshing together?
Yeah, I know that age-old saying, opposites attract.
Opposites attract.
All right. So what it took to figure out the answers to those two questions was a little bit more collaboration. It turns out that a female scientist, for once here, Irene Joliot-Curie.
Go Irene.
I don't think she's British either.
No.
She actually found that there were a certain kind of particles if she created that she could create by shooting the alpha particles at beryllium. So she actually found these particles flying out of beryllium when she shot beryllium with alpha particles, but she didn't know what they were.
Is this the lady, the two Currys, the Mr. and Mrs. that were scientists over in France?
Yeah, she's actually the daughter of them.
Oh, she's the daughter of the two.
She's
okay.
the daughter of the two, yeah.
All right.
Madame and Mr. Curie. I forgot their names.
Joseph?
Joseph Curie, maybe?
Didn't Mom die of radiation poisoning? X-ray poisoning?
I believe so. She loved her work.
I think he got hit by something, but...
Yeah. Well, she's a glowing example of a great scientist. All right. So, like a great scientist, Irene actually publishes her data, and James Chadwick, a British scientist, sorry, actually figures out, he reads what Joliot Curie has written, and he realizes that this beam of particles that's being created is not affected by electromagnetic fields. So he does basically the same experiment that Thompson did.
Okay.
He uses a magnet on them to see if they bend, and they don't bend. So therefore, he realizes that their charge must be neutral, and he gets credits.
Oh, he finds the neutron that is also in the nucleus.
So because Joliot Curie was a good scientist and didn't know about it and published it, she doesn't get credit for discovering the neutron.
Oh.
So on a test, if we ask you, who discovered the neutron?
Chadwick.
Yep, it's Chadwick. Unfortunately, this is a very... I don't know if this is male-centric or
Yeah,
if this is just... Yeah, it probably is. And that's why I like to talk about this right now. Is I think Irene Joliot Curie deserves a little bit of credit here.
Yeah.
Because she's the one who figured it out. She's the one who found it first.
Okay.
All right. So what that means is that our previous problem of mass is solved. Because this neutron actually weighs something. It moves a paddle wheel also.
Oh, so the proton and the neutron that is located in the nucleus is the bulk of the mass of an atom.
Exactly.
It's the two of them together.
Because the neutron has a lot of mass, it's thought to be located in the nucleus
And
also.
the bulk of the volume is the electrons outside the nucleus. What do we say? Solar system?
Solar system.
Revolving around. Oh,
it looks a bit
that.
like that.
There you go.
So basically you've got protons, you've got neutrons, and you've got electrons. These electrons are in concentric circles in these orbits. So that is it.
Yeah.